Okay, as I told you, there are two types of comparison tests. The first one was a direct comparison test, and we looked at that. Now there's a limit comparison test. Sometimes people like this limit comparison test a little bit more just because it's algorithmic. You don't have to try to come up with a comparison and determine how they relate to each other. It's an algorithm that you pull out. So let's write this out. We're going to let our series A sub k, oh my, and the series B sub k be series with positive terms. And and is that word. And we're going to let this happen. The limit as k approaches infinity of A sub k over B sub k equal L. All right, so it's a limit comparison test. So lo and behold, right, we're taking a limit. So let me scoot this up a little bit here. When I'm looking at L, there are three criteria associated with L. So you just take this limit. Again, B sub k is still going to be the comparison. And I'm still looking at this comparison in terms of the P series. So the same setup is happening here. So you're doing the exact same setup. So to start off with these two, you're still making this one to compare with, but you're going to take the limit of it, and that's the thing. So if, here's first criteria, 0 is less than L, which is less than infinity. That is, L is a finite positive number. L is finite and positive. Then the series A sub k and the series B sub k either both converge or diverge. So the same thing that happened with our integral test, right? This just means same behavior. So we want to look at our comparison with the P series, right? Then if you come up with just a number here with my limit, then you get same behavior. That's what that just said. Okay, number two here is if L equals 0 and B sub k converges, then, oh my, then your series A sub A also converges. All right. If L equals infinity and B sub k diverges, then you guessed it, A sub k also diverges. All right. So if you get a number, same behavior, whatever's happening with your comparison. If your limit is 0 and B sub k converges, so both of these criteria have to be met, then your original also converges. If your limit's infinity and B sub k diverges, then your original also diverges. All right, let's do this thing. We are going to use the limit comparison test here if I have something that's not as easy to do a direct comparison test with. For instance, if you have k is going from 1 to infinity of 5k to the 4th minus 2k squared plus 3 over 2k to the 6th minus k plus 5. Now you're not going to try to direct comparison that, right? Look at this business. You got all this minus k minus this. What? I am not doing that. I'm not trying to figure out how this all pans out. You do a direct comparison if it's an easy direct comparison. You got this big, huge polynomial that you're digging on. You're not going to try to go through that and figure out which one's bigger and which one's smaller. No thanks. This is where you do your limit. Your original 5k to the 4th minus 2k squared plus 3 over 2k to the 6th minus k plus 5. And then you're still looking at that lead behavior. So your lead behavior here, if you want to put that coefficient, great. If you don't, I don't really care because it all pans out. You have 5k to the 4th over 2k to the 6th. Now, you know what I just realized? We have not talked in this little 10.5 business here about our divergence test. What's always our first thing that we go for? Divergence test. If I take this quick limit, what does it go to? 0. Because you're looking at your lead behavior. It's bigger on the bottom than it is on the top. Whenever I'm going through and working this out, then I know that this whole thing, because that grows faster, is going to be 0. Okay, so I know the divergence test is out. Then we choose a different test. Anytime you have this polynomial over polynomial, that should be saying comparison test to you. That's our defining characteristic. Even if it's a tiny little polynomial over a polynomial, that is your defining characteristic here to say comparison test. Alrighty then. Then I take a limit as k approaches infinity of a sub k, which is my original, over 2k to the 6th minus k plus 5. And I am dividing that by b sub k. Now, what do you do when you divide fractions? You multiply by the reciprocal. So I'm actually multiplying this by 2k to the 6th over 5k to the 4th. Multiplying by the reciprocal is the same thing as dividing these, right? So you multiply by that reciprocal. Now, you distribute. So, I'm going to put a different color on here. Whenever I work that, I can't cancel anything. Everything in here is touching a plus or minus. So you cannot cancel these because of that minus sign. So if some of you tried to do that, tap the brakes. Remember, anything touching a plus or minus is off limits. So what you have to do is go ahead and distribute and see what's going down now. Give me back to blue. So I now have, oops, I'm going to take it down here. We work math vertically. 10k to the 6th minus 4k to the 8th plus a 6k to the 6th. Oh, just distributing, right? If I take this and multiply it by each term, I'm going to take this one and multiply it by each term. 10k to the 10th, which is why I'm cuckoo-ca-choo. You guys are probably hollering at me. Good job hollering at me. Like bases, you add the exponents. That's 10k to the 10th up there. Minus 5k to the 5th plus 25k to the 4th. When you take your limits, you're taking that lead behavior because these are the same. Then I take the coefficients. 10 over 10 in this instance is equal to 1. Because 0 is less than 1, which is less than infinity, that tells me that I have the same behavior. So we got to figure out what is our behavior. If I simplify this rational expression, I have 5 over 2k squared. The numbers nobody cares about. This is 1 here over 2k squared. That looks like a 51. Which is p is equal to 2, greater than 1, converges. If my comparison converges, I'm going to keep that on there because I'm afraid if I print these notes off, you're going to look at that and go, what the world did that girl do? So my p here is 2, which is greater than 1, so I know that converges. Because my comparison converges and my limit is just a positive finite number, whatever that is, in this instance 1, then I know my original also converges because it's same behavior. I'm just going to write the series because that's a big one. Converges by the limit comparison test. Remember, when you show all your work, you want to finalize that statement, right? Therefore, this 3 dots just means therefore. That's just a math symbol for therefore. The series, you can either write out the words the series or you can write out what the actual series is. You have to state if it converges or diverges and how you know that. There's 3 parts to your answer. Either writing the words the series or writing it out. State if it converges or diverges, and then how you know that by that particular test. All right. So your limit comparison test, you just take that, you just divide those 2 fractions and you go with it.